It is a definition of chemistry that it's the study of all things which have a mass and take up volume. But where does the mass of a chemical substance come from? All matter is made up of atoms, and the atoms of different elements have different masses. Hydrogen is the lightest element with a relative atomic mass of 1. That number there, by the way, is not the atomic mass, but we'll come to that in another video. Oganesson is the heaviest known element, and that has a relative atomic mass of 294. Helpfully, the periodic table of elements lists the relative atomic masses of all 118 known elements, as well as other useful pieces of information. And so, if you needed to know the mass of an element to do some larger calculations, such as some we'll encounter later in our studies, you just find a periodic table, and so long as you know which of the two numbers listed is the mass number, it's always the biggest number, by the way, then you can just use that. But where does that number come from? And how is it calculated? You probably remember from your basic chemistry studies that an atom is made up of protons, neutrons, and electrons. And if you can't, you should go and take a look at some revision videos about atomic structure to help you. Protons and neutrons both have a mass of 1. Electrons do have a mass too, but at GCSE we say this is pretty much 0, certainly negligible, and it doesn't contribute to our calculations or our understanding of relative atomic mass, either at GCSE or A-level. The mass of an atom, therefore, is the sum of the total number of protons and neutrons found in its nucleus. A GCSE periodic table of elements shows that most of these elements have a nice, simple whole number for the relative atomic mass. But what about something like chlorine? The relative atomic mass of this element is given as 35.5, but if the mass of protons is 1 and the mass of neutrons is 1, how on earth do we have a non-whole number for our mass? In fact, the reported number in the periodic table of elements is not the exact mass of every single atom of that particular element. A chlorine atom contains 17 protons. Every single chlorine atom in the universe contains 17 protons. However, some of these chlorine atoms contain 18 neutrons and some contain 20 neutrons. Atoms of the same element which contain different numbers of neutrons are called isotopes. If they have different numbers of neutrons, then some of the different atoms of chlorine must, therefore, have different masses. Very clever scientists have worked out that 75.77% of all the chlorine atoms in the universe have a mass of 35, and 24.23% of all the chlorine atoms in the universe have a mass of 37. It would be too complicated to put all of these different values into a periodic table, so instead, the given value that you see is an average made up of all of the different masses of all of the different isotopes of that particular element. You're expected to be able to calculate this value given some specific data. Let's use chlorine to show you how to do it. To calculate the relative atomic mass of any element, you need to be given the different masses of the different isotopes of each element and the relative abundance of each isotope of each element. You will be given these. For example, I've already mentioned that 75.77% of all the chlorine atoms in the universe have a mass of 35, and 24.23% of all the chlorine atoms in the universe have a mass of 37. We have two isotopes, one with a mass of 35 and one with a mass of 37. We also know the abundance of each isotope. The general formula to calculate the average relative atomic mass for any given element is given in this equation on the screen. The mass of isotope 1 multiplied by the abundance of isotope 1, and then you add that value to the mass of isotope 2 multiplied by the abundance of isotope 2. Once you get that value, you divide the number by 100 to give you your average relative atomic mass. Here's an example showing our chlorine values to show you what I mean. I put the values into the right places in my equation. I do the calculations inside both brackets, then I add the two values together and I divide by 100. There, the value is very nearly 35.5. It doesn't matter what element we're talking about, the formula is the same. You just substitute in all the values you were given for mass and abundance. If there's 3 isotopes, then you do the same again. For all the possible isotopes, you still divide by 100. Now, here's some for you to try. 3 examples. Our first is bromine. It has 2 main isotopes. 50% of the isotopes have a mass of 79, and 50% of the isotopes have a mass of 81. Using that information and the general equation on the screen in front of you, calculate the relative atomic mass of bromine. Pause the video, have a go, then see what the actual answer is, and if you've got that right, go on to the next 2. If you haven't, go back through the video, look through the worked equation again, and then have another go. Hopefully, it will all make sense. Okay, you've paused the video, you've had a go, I sincerely hope, so here are some answers. I've plugged in all of the relevant details into the equations to show you how you come up with each of the answers. The final answer should be 80. The relative atomic mass of bromine is 80. If you got that right, move on to the next, which is copper. The final result that you should get is 63.55, and there are the equations and the data to show you how to do it. If not, pause, go back, review, and have another go. The next one is the hardest. Here we have carbon, which has 3 isotopes, but you do exactly the same with each of the different isotopes. You're just doing 1 extra. The end result should be 12.011. You might get asked a question of this complexity, but it's not very likely. But if you can do 1, you can do the all. Here, though, is the equation you need to memorize. Just that. Very good luck. There's lots of other chemical calculations, and there'll be lots of other videos to help you. Until then, good luck with your studies, and see you soon.